Okay, good afternoon, everyone. Uh, Let us continue from where we left in the last class. Now, in the last class, we have seen regarding the push and the pop operation of stacks, and then we also talked about the time complexity of each push and the pop operation. Now, in the same way, if you consider the stack, let us look at this part. So, last class we have seen the operations of push or add or pop or delete on stacks, and this stack was represented using arrays. So what all we performed here, like top equal to top minus one and stack of top is nothing but we are performing these operations based on the representation of these stacks and arrays. Now the next thing is the same operations, that is push and pop on stacks, can also be applied when the stacks are represented as linked list. Now, if you remember in data structures, linked list is one of the data structures which has nodes, and each node has the data or the element, and the other part is the reference or the pointer to the next node, immediate next node. So if you consider this here, we have the stack. What we are saying is this stack is represented as a linked list. So the element 84 over here has a link to the next element, which is 47. To the 47 has a link to the next element, that is 21, 96, and 50, and so on. Now, linear list, in linear list, what happens is you can insert the elements at at the beginning of the linear list, or I mean the linked list, or you can also insert the elements from the end, as well as you can insert the elements from the I mean, you can delete the elements from the beginning as well as from the end of the linked list. Now here, since the operations of whatever adding or pushing or deleting or popping is performed at only one end in stack, so if we represent the stack using linked list, what we do is we usually say that we will be deleting, or we will be adding or inserting or pushing, and we will be deleting or popping or removing the elements from the front of the linked list or from the beginning of the linked list, because it's the only one end is open in stacks. So whenever stacks is represented using linked list, remember that instead of front or the head node, we call it as a top node, and insertion and deletion happens from that end. So here what we are doing is, if we have to push or add an item, temp is the new node created. So this is a node will be created here, temp. Initially top is pointing to the first node, and then we say that these are all the other nodes. So actually the arrows should have been on the opposite side. Sorry. There is a mistake in the representation here. The arrows should have been on the opposite side. Arrows. So yeah, this is the correct way. This is the correct way. So I'll just let me I let me make some changes here. The arrows actually has been in opposite direction. So again, it's going to be a problem in trying to understand. So let's now this is correct. Sorry about it. So the top or the head position is always the front or the beginning of the linked list when stacks are represented. So we say that we will be adding or removing the elements from the top, that is the front of the linked list. Now a new node will be created wherever a new node has to be added or new element has to be added. A new node known as temp will be created. So this will be temp. A new node is created, although I don't have any value here, it will blank. Then we check that if temp is not equal to null, that means they are, some elements in the node we can insert temp. Obviously, there is a space in the memory, that means. Though we usually don't have this operation, you might not have seen in stacks when you represented them using linked list. You may not have seen this condition here. But here what we have is, because we are designing an algorithm, we have to take into consideration every aspect and scenario. So what we are saying here is, if temp is not null, means temp is created, a new node is created. That is, there is a capacity in the memory that we are able to create a space. Able to create a node that we have so much space. So anyway, if there is a space, that means we can create a node. Node is created already. Then temp arrow data, whatever item you want to insert. Suppose if I want to insert, let's say 20. So I'll assign data as 20 over here. Then temp arrow link, this temp arrow, this link, what you're seeing here, this link should point to top. So top will be here. And then this top will move up and will point to this node. So then return true. Else, if we are not able to, this temp cannot be created, then that means there is no space. So we say out of space and we return. So this is not the case when you have defined or created the stacks using linked list in your data structures. But here we have to take care, or the algorithm says that there should be a memory available. Only then we will be able to create a node. So whatever the reason might be, we will create a temp as a new node, and then its data will assign, and the link will assign to the top and move top to the point to that node. So a new node will be added at the front. In the same way, what happens is delete also is the same thing. Now here what happens is delete or pop method, we check if top is equal to null. If top is equal to null, means it is not pointing to any node, that means the stack is empty. Then we return false. Now else what happens is, if suppose this is top, this part is top. Now suppose this part is top. Now suppose this is top, 15 is the top element. So we retrieve the element from top arrow data, we get the item there. And we will take a temp as the reference variable, or a variable, or an object, I suppose, which stores. So 15 top and temp will be pointing, both will be pointing to 15. Then top equal to top arrow link, that is top will move to the next element, that is 96. And then you can delete temp, that is element 15 can be deleted. So this is how stack works, or the operations of stack using linked list works. Now you have already seen this in data structures. We just have to brush up these aspects. Now let us try to find the time complexity of these two functions or algorithms. That is, we already had seen last class time complexity of add or push method or algorithm and pop or delete algorithm when stacks was represented as arrays. Now, in the same way, even here, if you look at this, let me take a pen. If you look at this method, then this add method is when stacks are represented using linked list. So this statement is going to take unit of time. This is if statement, obviously it takes unit of time. Anyway, I'm just to write it. There is no loops. This is a basic primitive statement, takes unit of time. Even this statement takes unit of time. Even this statement takes unit of time, because these are all basic statements. Then we don't have to bother about this out of space and all, it doesn't matter. Even if we add up, it doesn't matter, it's going to take constant. So the total is 1, 2, 3, 4, 5. So it's nothing but when we have 5, this 5 is order of 5, which is nothing but O of 1, or we say that it's constant time complexity. So it's the time complexity of this algorithm is constant. Then let us take the next one, the delete method. And delete method, these statements are primitive statements. Doesn't matter if, because it takes only 1 unit of time. I mean, though it executes if there is no element, but the main important statements are these statements in the else part. So this statement, this primitive statement, take 1 unit of time. Even this takes 1. Even this takes 1. Even this takes 1, as well as this takes 1. So on the whole, we have 1, 2, 3, 4, 5. So instead of that, you have 5. It's constant. So instead of that, what we say is it is order of 1, or big omega of 1. So this is, so remember that whether stacks are implemented using arrays or whether they are implemented using linked list, the add and delete operations both will be taking unit of time, that is big O of 1 or order of 1 as the time complexity. And let us move further. Let us talk about queues. Now, if you here the textbook or the syllabus more focuses on circular queues rather than queues. And with respect to stacks, in comparison to stacks, here we are not talking about whether the queues can be represented using linked list or using arrays. We don't have any problem when the queues are represented using linked list. But there is a problem with respect to memory utilization when queues are represented using arrays. So here, the textbook or the syllabus, we only concentrate about queues through which the elements can be stored and the operations can be performed based on the array representation. Because there is no problem with respect to linked based representation as far as the memory is concerned. Now what happens is, if I go back, let's say that, let's see the first slide. This is, let's say, this is our queue. Now what happens is, in queue, the operation, you all know that the elements are inserted at the rear end and removed from the front end. So in normal basic operations when we perform in queues, when initially front and rear will be pointing to the initial part, then rear will be incremented and an element will be added. Front will be pointing to that node. So first time the front and rear will both be pointing to the same element because there is only one element at the initial state. Then rear will be incremented and then next element will be added. Again, rear will be incremented, another element, so on and so forth. Let's assume that we have 5 elements here. Now, in an array, obviously, we all know that there is a capacity for an array. In an array, there is a size for an array. So the maximum number of elements that we can store for a stack or a queue is limited to that size. And in stack, there is no problem because we will always insert the elements from the rear end as well as remove the elements from the rear end when array is considered. But whereas in queues, we insert from the rear end and remove from the front. So now I have started inserting it. And then suppose if I insert another element, let's say 16. So rear will move here. So this will be rear. Then 17, I add 18, I'll add. So ultimately, this rear is going to come here. This rear is going to come here. That is, rear will be pointing to this. Now, if I try to insert another element like 20, will I be able to insert? No, because the size of the array is full. So the whole capacity is exhausted. Now, if I remove an element, say 84 is removed, so what happens? Front will not be pointing to this element. Front will be pointing to this element. So this will be empty. If I remove another element, 47, let's say, so front will not be pointing here. Front will be pointing to this node now, and these two cells are, what do you call it? They are empty. But suppose if I now try to insert an element in the queue, I have to increment rear. When I increment rear, there is no sequential space here available here. There is no space available here. Array size of the array is exhausted, so I will not be able to insert an element, even though there are some spaces empty at the beginning of the queue, or at the beginning of the array. So I will not be able to insert the elements now, even though I have space, because the rear has reached the capacity or till the end, the length of the or the capacity of the array. So I cannot increment an rear pointer and insert it, because I will not be able to insert in that place. There is capacity is has reached that limit, even though I have some empty spaces or empty cells remaining in the array. So this is the problem. So in that case, what we do is, we instead of this one, what we consider is, this is like a circular queue. We consider circular queue. It's a cycle. So when rear is incremented, rear, instead of creating a new space here, this rear pointer will come and will be pointing to the first element. So this will be rear. So these type of queues are known as circular queues. So that is what we have it here. That is what we have it here. Circular queues. So in circular queues, what happens is, you start from zero. Let's say if you start from 0 or 1, whatever it is, I can store element J1, J2, J3, J4, and all these things are considered in circular fashion. Two, last element will be n minus 1. Now I have started inserting here. So I can say that this is the front of the circular queue, and this is the rear of the circular queue. Now what I can do, I can start adding element here, element here, element here, till I can fill it up. So rear suppose can point back, and I can remove. So the cycle continues for rear. I can continue the rear cycle, or start deleting, or even start inserting. Now obviously, when all the elements are full, that means even this is if rear is pointing here to the cell, all the cells are occupied, that then queue is full, obviously. But suppose if I start deleting, so front will not be here. I delete one element, two element now, so a front will point here. So what happens, even if things are full, these two elements might be empty, and rear, if you increment the rear, since it's a circular queue, rear will be pointing here. So this, it forms like a cycle there. The front and rear can move along. But remember that if all the cells are full, even here, we cannot insert. But the circular queue gives us the flexibility of incrementing the rear value and coming, using the empty cells which will may be there at the beginning of the queue. Now, this is another thing, example. So what it says is, there is no fixed front and rear. Now this keeps on moving. You can, I mean, store elements from this also, this 0, and then n minus 1, n minus 2. That way you will be able to store it. So circular queue, what this diagram is same as this. There is absolutely no difference, except that the elements are stored at different locations in both of them. So this is what is the circular queue. Now the operations, obviously, it is known as enqueue or add on queues. And remember that we are taking circular queue into consideration here, and stack based representation. So enqueue is to add element in the queue. So whenever you are adding element, you will not just do rear plus 1, but you will do rear plus 1 mod n. N is number of, or the number of cells, or the capacity of your array. So mod n means whatever rear value you start increasing, mod n will give you the remainder one. So you will be within the range, and the rear pointer will not exceed the array, but once it reaches n, it will now be pointing to the 0th element. So mod n is used to move in circular fashion, move the rear pointer in circular fashion, or rear index in circular fashion. Then we will check if front equal to rear. That means obviously front is equal to rear. When the rear comes front, both are running. That means all the cells are occupied. So we say that queue is full. Otherwise, if front is 0, that means there is no elements in the queue. Queue is empty actually. So rear becomes n minus 1. Else, if front is there, then rear equal to rear minus. Now here there is still, when front equal to rear, we will not be able to insert the element. So Q is full. Well, that is one point. And if Q is full, now what we can do? We just cannot. Front is equal to 0. That is only first position. Front is at first position, and rear is also has a rear still. So rear, we just don't add this, make this rear. Rear we make it n minus 1. We make it back. So actually, rear was at this place. Rear was at this place, and by performing this step, rear was pointing to this place. The rear was pointing. Assume that this is also filled up with J0 something, pointing to this step. Now, once if front is 0 itself, front is also pointing here. If this is the front is also pointing here, then whatever rear was incremented, we will get back rear to the original position. Because again, next time also we have to increment and perform the mod operation. Else, if front is not 0, front is not 0, what happens is rear will be rear minus 1. So if front is pointing here, suppose if F was here and R was here, rear were here, R rear was here. So with this, what happens? Rear will be pointing to this part, front itself. Now front is not 0 means we have to get back rear to, rear was 3 means rear minus 1, which is 2. So again, rear has to come back here so that in the next operation, we will be able to know what is there. So in this case, both, in this scenario, we are not able to insert any item because the queue is full. If queue is not full, then rear, this item is assigned to the index wherever rear is pointing. Now rear is actually pointing to this. Using this expression, the rear points to that index, and we return true. So this is how we implement the NQ method to add the nodes. I add the elements in the queue when a queue is in circular fashion, represented using stacks. Represented using arrays. Now, same way as we have added, we also have a method known as delete, that is DQ method. In this DQ method also, we see whether front is equal to rear or not. If it is equal to, that means queue is empty. There are no elements, both are equal. If not, then we decrement front, we increment front because we are deleting from that. But we use mod 10 because it's a circular queue. The whatever increment happens, it has to be mod so that we end at, we are within the range of indexes for our circular queue. And that is the front index we get, and we retrieve the queue of the front, whatever element is there, we return true. So this is very simple rather than adding the elements. But always remember that just don't just try to add rear plus 1 and we just don't do front plus 1 as in normal queues. But since this is a circular queue to save space, we perform the mod operation both the ways in rear plus 1 mod n as well as front plus 1. Over here, as we have seen, rear plus 1 mod n as well as front plus 1 mod n. So we have mod n so that we are within the range of the number of elements what we have in the array. So this is what is circular queues about. So remember that we have not looked at the stack representation. We have looked at the array and linked based representation of stacks, but we only looked at the array-based representation of queues, and that too with respect to circular queues because we have a problem of storage or memory utilization. Anyway, there is no problem with respect to the queues which are represented as linked list, using linked list, because an operation, there is no problem with the memory because one operation, that is enqueue or adding the element or inserting the element of queue, is performed on the from the front end, and sorry, inserting is performed from the rear end, and removing or dequeuing is performed from the front end in the linked representation of queues. So this was all about the basics of here our queues. Now we'll just take up another topic for today, that is again the refreshment or refreshing the concept of elementary data structure. So we will continue with the topic of trees. Now trees is a non-linear data structure. Remember that. Stacks and queues are linear data structures. Linear means there is a relationship, a sequential relationship between elements. Like uh, in an array, you take the array elements in an array. What happens? There is whatever element you have, there is a sequential relationship. One element, if you take, you can say that that element occurs after or before some element. Obviously, there will not be a before element for the first element itself in sequence in linear data structures, as well as there will not be a after element for the last element. So that's, I mean, the relationship is sequential or what we say linear in terms of the elements. So there is before and after relationship. That is why those are stacks and queues are known as linear data structures. But trees are non-linear data structures. There is no sequence as such. There is no before and after relationship. But here there is a hierarchical relationship. That is why it's called as non-linear data structures. Hierarchical relationship. The relationship here is not before and after, but relationship here is above and below. It's a hierarchy, above and below relationship. So if you see, if we take this node, let's say C, there is no before and after. We cannot say that B is before C and D is after C. There is no before and after relationship here. This is a non-linear data structure, but it has above and below relationship. That is, A is above C and G is below C. So there is an above and below relation. It's a hierarchy there, like just like a parent-child relationship. So for C, A is the parent of C and G is the child of C. So it's a hierarchical relationship, and it is known as so trees are known as non-linear data structures. Now there is a special node here. That node doesn't have, and there's only one special one node which is special and which doesn't have its parent. That is known as the root node. So here A is the root node. It doesn't have a parent, and every tree will have a root node. If there is a node, then definitely there will be a root node which does not have any parent. Then there are several other normal terminology used in trees. That is, the nodes which does not have any children are known as leaf nodes, or external nodes. So here in this case, G is a child node, F is a child node. So G, F all are leaf node. G, F, M, I, J, L, K, all these are leaf nodes or external nodes. They don't have any children. Then the nodes which has children, like for example B, E, C, D, these are known as non-leaf nodes or internal nodes. They have children. Even node A is an internal node or non-leaf node, but it has a special property that is doesn't have a parent, so it is known as a root node. Then we need to see another thing that since it's a hierarchical data structures, there is a levels. The elements are not before and after, but the elements are placed at levels. So root node will be at level 1. Then its children, that is, in this case, A is root node. Its children B, C, and D will be at second level. Its grandchildren, that is E, F, G, H, and so will be at the third level. And subsequently, the in the hierarchy, next level will be the fourth level. So level goes on starting from the root node, and then its children in the hierarchy continues. Now, there is another up from trees. Now, if you look at the previous tree, a node may have more than, may not have a children, that means it's a leaf node. If it has children, it may have one child or more than one child. So in this case, if you see node B has two children, whereas node D has three children, node C has only one child. So if we consider, there is special kind of trees known as binary trees, where a node can have at most two children. At most two children. That means a node of a binary tree can have no children, no child, or it can have one child, or it can have two children. Not more than two children. At the most two. So in this case, if you look at this side, the larger graph, sorry, larger tree, A has two children, B has two, D also has two. H, I, E, F, and G are leaf nodes. They don't have any children, so this is a binary tree. And the level of this binary tree is A is on first level, B, C second, D, E, F third, and H and I at fourth level. Let us look at this tree, which has only left child. So here A is there, it has one child B, B has one child C, C has one child D, D has one child E, and E is a leaf node, doesn't have any children. So is this a binary tree? Can anybody answer? Is this a binary tree? Just type it in chat. Type it in the chat, man. Is it a binary tree? Anyone? If you are listening, obviously. If you're not listening, then I can't say. Anybody? Anyway, it doesn't matter. I hope you, again, people look at the recording and then try to understand. But anyway, right now you people are not awake. So let me continue the class. You people can go through this later. Anyway, this part, this is also a binary tree because every node has at most two children. 0, 1, or 2. Not more than 2. So this is also a binary tree. But this is known as, since all the nodes have left child itself, it is known as left skewed binary tree. Left skewed binary tree. But you can see that the number of levels increases here. Here, the levels of this binary tree are 5. The 5 levels in this binary tree. Whereas, if you consider this binary tree, it has only 4 levels. Let's move further. Let's look at another definition here, which is a full binary tree. A full binary tree means every node will have, every internal node or non-leaf node will have exactly 2 children, and all the leaf nodes are on the same level. All the leaf nodes are on the same level. Though there is also a formula also through which the full binary tree is described. Now what it says is, in terms of height, it says full binary tree of height h will have 2 power h minus 1 nodes. Exactly 2 power h minus 1 nodes. But in general sense, what we define with the full binary tree, what we say in the theoretical terminology is that a full binary tree will have all the non-leaf nodes or internal nodes will have exactly 2 children, and all the leaf nodes are on the same level. So you can see all leaf nodes 1, 2, 4, 5, 6, 3, and 7, all of them have exactly 2 children, and all the leaf nodes are on the same level. Then let us look at the representation of this binary tree. And what we need to do over here is that we need to where is the pointer marker? I'll just take a marker here. Okay. Now we can use arrays as well as linked list to represent binary trees. Let us first look at how to represent using arrays, that is sequential representation or sequential using sequential memory location, representing binary trees. What we will do is we will start numbering the nodes from the top to bottom and in each level from left to right. So from top to bottom means we'll start with A as we will number it as 1. In the next level, top to bottom, next level, yeah, from and within the level from left to right. So we'll number node B as 2, C as 3. The next level from left to right, so D as 4, E as 5, F as 6, G as 7. And then next level 8 for H and 9 for I. So we start numbering nodes from in level order, that is from in level from top level to bottom, and each level from left to right. And then since we are using arrays, arrays has indexes which we start from 1 to 15. Obviously, this is not language dependent. Depending upon language, array may start from index 0. But we are considering this is an algorithm, designing an algorithm. So we are considering array starting from 1, index 1. So A is there, which is at what have we labeled? We labeled it to be 1. So it will be stored at index 1. Same way B will be stored at index 2, C at index 3, because that is how we have labeled it. D, E, F, G, H, and F, G, H, and I. I is at 9th index. So here we are storing at the 9th level we have given, 9th index we are storing. So this is how sequentially we represent the nodes in an array using sequential representation. Now let us look at this. Now what happens here? How is it placed? There is also array representation, sequential representation. And this was easy because all nodes were filled up at positions. But here, this is a little difficult. So what we say is A, we number it 1, label it 1. B, next level, we label it as 2 node. But in this level, B level, they could have been a node here. They could have been a node here whose label would have been 3. We consider a full binary table. Then at C, so A only 2 nodes can be there, B and any other node, but it's not there, so this is labeled as 3. So C will be labeled as 4. When C is labeled as 4, why 4? Because 2, there is nothing at 3, so 4. And then B here, it could have been a node over here, which would have been 5. There could have been a node here, which would have been 6. There could have been a node here, which could have been 7. Then comes D, which is 8, labeled as 8. So if you see A is at index 1, B is at index 2, then 3 there is no node, so we make it blank. 4th index we have C, which is labeled as C. 5th we don't have anything. 6th we don't have anything. 7th we don't have anything. 5th, 6th, and 7th these are blank, but we have to label it. Then 8 we have D, we have at the 8th position. The same way they could have been a node here and 2 nodes of this, 2 nodes of this, 2 nodes of this. And finally, E will be at the 15th place. So the entire thing is represented as a full binary for labeling purpose. But when we actually, for labeling purpose, we consider this as a full binary. But it's not exactly a full binary tree. Only for labeling purpose we are considering, and rest of the nodes of the tree will be empty, so we don't fill them up. So now here what is happening is, if the tree is a left skewed, you can find that there's so much memory space has been wasted. That is, to store here, in this case, to store 9 elements, mean 9 memory location would have been enough index for an array. But in this case, if you look at it, if we have to store these 5 elements, we need 15 memory locations, and most of the memory locations are empty. But we need 15 memory locations. So array-based representation of a binary tree or sequential representation of a binary tree consumes lot of memory. It actually wastes a lot of memory because many of the cells, if it's a right skewed or left skewed binary tree, many of the cells will be empty. So there's a problem with respect to binary trees representation using arrays. So we move on with the next type of representation, that is linked based representation. Now obviously we will try to talk about this linked based because we have to go into detail of this linked based representation. So we will continue with the linked based representation in the next session, next class. So now if you have any questions or so, we can clarify them, or else we can end today's session. Any questions, or should we end the session? Okay, then we will end this session. Please log off. No, क्या जबरदस्त रहेगा.